Okay, welcome to GADAPS. Today we have Mingmin Shen, who is going to talk about some counterexamples to the Hodge conjecture. Okay, Mingmin, you can go.
Yeah, thank you. I would like to thank the organizers for the invitation. It's a nice opportunity to speak here. So today I will talk about some examples, counterexamples to the integral Hodge conjecture. So let me first quickly recall what the conjecture is about. The integral Hodge conjecture. Okay, so this starts with some, let's say like a Hodge theory. Okay, so now if we have X, which is a compact Kähler manifold, then we have the following decomposition. So HK of this Betti cohomology group with Z coefficient. If you tensor with the complex numbers, there is a canonical splitting into the PQ pods. Say P plus Q equals K, and then PQ greater than equal to 0. Satisfying the condition that so such that the HQP, if you take the complex conjugate, you will get just the HPQ. Okay, the complex conjugation comes from the complex conjugation on the complex numbers on this side. So basically, this you view this as like a real part, and here you can apply complex conjugation. Okay, this is called a Hodge decomposition. So, in other words, so when is like some cohomology group or some like a Z module has this property, we will say it has a Hodge structure of weight n. So in this case, we can see like the HK of weight k. So the HK of a compact Kähler manifold actually has a Hodge structure of weight k. Now, we will be mainly interested in the case where X is a smooth projective variety. So we will be interested in a smooth projective variety over the complex numbers. Okay, this is the Hodge decomposition. Now, then we have an interesting map called a cycle-closed map. Cycle-closed map. Okay. Now we start with X over C, and this will be a smooth projective variety. Okay. I take the dimension X, say it's D. Then if we have a Z, which is inside X, this is irreducible closed subvariety. Codimension equal to K. Okay. Then we can, once we have this, because we can just think of Z as a topological and space inside X. This actually defines a topological cycle, and that gives a clause inside H 2D minus 2K on X with Z coefficient. Okay. Well, here that it's essential that Z is an algebraic subvariety, so it has on the smooth part it has a canonical orientation, and the well, then you can well do a little bit to deal with the singular part, and you actually get a clause like this. Now, then you can use the Poincare duality. So this is Poincare duality. It goes to H2kx with z coefficient. Okay, so in this way, you can see for irreducible closed subvariety, I actually get a cohomology clause of with 2k. Okay, now then we can define the zk to be the x. This is a free abelian group on irreducible closed subvarieties of codimension k. Okay, then we can define a map called a cycle class map on X. It goes to from zk x to h2k of x z. Simply you take a linear combination ai zi. This goes to the linear combination of the classes. Okay. Now it's actually quite an easy fact. You can check if we think about the H2k, the decomposition, this you can map to H2k of an xz tangent with c, and you have a class z inside here. If you map to this side, you take z, of course, tensor with 1. It turns out that this is inside the kk part of the decomposition. Once you take an algebraic subvariety, you always hit in this part. Okay. Then we can define. So this is like the definition 1. So alpha inside a class H2k of x z is an integral Hodge class if alpha tensor 1 as an element in the C coefficient cohomology group, it sits inside H k of x. Okay. And we can okay, so this is the integral Hodge class. Then you can put all integral Hodge classes together and we'll form a group called Hodge with degree 2k of x z. This is the group of all integral Hodge classes. Okay, and we can see that then we can state the integral Hodge conjecture. So the statement is the class. So this is the integral Hodge conjecture. So the class map on X from zk x. Now we know that the image will be inside the group of Hodge classes. So this is surjective. Okay. Now it turns out that this conjecture is actually false, but we still call it a conjecture for historical reasons, sort of. This. So the first counterexample is was discovered by Adia Hitzbrug. This was in 1962. And well, that was the first counter example. And then later, many counter examples were discovered using different like theories. So here I'm not mentioning those theories and names. Actually, a lot of mathematicians made a lot of contributions in this direction. So then, in the positive side, so here we also have some positive results. Firstly, of course, we know that this is always true for k equals 1. So for codimension 1 cycles or divisor classes, we know that integral Hodge conjecture holds, and that is called the Lefschetz 1-1 theorem. Then another example in this direction is this is true for X being, say, Calabi-Yau threefolds. And that was proved by Claire Voisin in 2006. Yeah. Okay. Now, what related to this talk is I will discuss some more recent counterexamples. And, some more recent counterexamples. So then I can state first, this was first constructed by Benoit Autumn. Published last year. So we let S be an Enriques surface So that's like a smooth projective surface which admits a tau double cover, and the double cover becomes a K3 surface. Now we let an X, maybe I use the E over C be a very general elliptic curve. Okay. Now, once we have these, then we can take the product. It still turns out that then the integral Hodge conjecture fails on E cross S. Okay, so that's like an example where the integral Hodge conjecture fails. Now, then, like a year later, I made some improvements to this. I stated. So again, I take like S be an Enriques surface over complex number. Now let X inside the P n plus 1 be a very general hypersurface of order dimension n. So here it's important that it's order dimension. That's the case where I can deal with. Okay, then okay, I actually in my result it can be made more precise. Like we can say which classes actually fails to be algebraic, and those classes are integral Hodge class because they are torsion classes. So let me see that. So alpha in H n x z and u inside H3 S Z. Well, this group is actually Z mod 2 Z. Okay, but then I take the generated the non-zero element. And this be the non-zero element. Okay. So now we can take the tensor product. The idea is that then the class I take the alpha tensor with U. So using the Kunis decomposition, you can view this as a class inside H. Now this alpha is in degree n and U is in degree 3, so I have n plus 3 x cross s. This is Z coefficient, and the class is not algebraic unless it's 0. Because the element U is two torsion. So if, for example, alpha is twice of something else, then this tensor is 0. So it automatically will be algebraic. But as long as it's non-zero, then it's never algebraic.
So there is no restriction on alpha, no? Alpha is just arbitrary.
No restriction, just some alpha which you make this class to be non-zero, then it's not algebraic. But this class is an integral Hodge class because it's a torsion class.
I see.
Yeah, so by definition, every torsion class is an integral Hodge class. Okay, so that's the main results I talk about. Now, then I will explain the main ideas behind the technique of the proof. About extendability and algebraic cycles. Okay, now let's do the following very simple observation. So I take U to be some open subset of a smooth variety X, and both of them are smooth. So smooth variety. Okay, now suppose I take some class on the in the cohomology, say it's 2k of U with Z coefficient. Actually, it can be any kind of general coefficient. Let's take a class here, and if say alpha equals the class of an algebraic subvariety, so for some Z inside U, this is an irreducible closed subvariety. Okay, if this happens, then there exists some alpha tilde, which is a cohomology class in the same degree, 2k on X with Z coefficient, such that this alpha tilde, when you restrict to U, you just get alpha itself. in general, for cohomology classes, this does not necessarily hold, but for algebraic classes, this will hold. Actually, it's quite simple. So indeed, we can take alpha tilde to be you take the characteristic closure of Z inside X, then you take its class. So this observation is very simple. It tells us that algebraic classes should have better extension properties. So as long as you have ambient sort of space which is smooth, then you can always extend. Okay. So now, based on this observation, then we can make the following.
Maybe a little bit. So a priori, Z is not compact, no? Because you take it in subvariety of U.
Oh yes, here to be more precise, I take like Z. This is not compact, but it's it's locally compact. So for this kind of we can write down this as a locally what's it called, locally finite kind of a topology cycle. So it is inside the Brillouin-Moore homology of some corrected dimension of U. Now, because U is smooth, then you can still have the Poincare duality between the usual cohomology and the Brillouin-Moore homology. So, yeah, so when U is like a complete, say, smooth variety, then the Brillouin-Moore homology is the same as the usual homology. But when it's non-compact, you can define this to be the homology of locally finite topological cycles. Then you still have the Poincare duality, and the cycle class still works. So that's the idea.
Okay.
Okay. Now, yeah. So now I will make this definition, which I will use later. So let pi this be a dominant morphism and projective morphism between smooth, like I say, complete smooth projective varieties. Okay. Now I let 0 to be a point of B. Okay. X to be the pi inverse, the fiber at 0. This should we assume this to be a smooth fiber. Okay, now we take some coefficient ring. This will be a commutative ring. So this, this ring will be the coefficient ring for our cohomology theory. So you can think of this as Z, or like Z mod NZ, those kind of usual rings. Okay, now, so I let alpha to be a cohomology class in H. Let's say Kx with R coefficient. So you have on this smooth fiber, suppose you have a cohomology class, and we say that alpha is extendable if the following holds. The first, we have needed some structure, so there exists a smooth projective variety say B tilde together with a generically finite morphism, dominant morphism from B tilde to B. And then we also need a preimage zero tilde in B tilde. Okay, there should be a preimage of the closed point B. Okay, so these are the structures we need, and they should satisfy the following condition such that, and therefore all resolutions x tilde of the base change of the family x prime, which is x plus b with b tilde, for all smooth resolution of this base change, there exists a cohomology class alpha inside hk of the whole space. Okay, now you want this to extend alpha. So in such a way, this alpha tilde is just, you restrict to x tilde over the point 0 tilde, okay, is the same as alpha. Of course, you needed to identify the fibers on the identification of x and x tilde 0 tilde. Okay, so in other words, now suppose I have originally I have some family for B. So this is the B, and this is the X. Now I have a point and I have a smooth fiber called X. Okay, I have some class on this closed fiber. It's extendable if we can find some so yeah, that exists. So we can find some B tilde. So this will be the B tilde. So generically finite, I have a preimage of the zero called 0 tilde. Okay, then of course the fiber here is identified with X using this diagram, and also usually by the base change you might get some singularities on the space. And what I do is I resolve the singularity. So this fiber is still here, and probably I get some exceptional divisor. Okay, once you do this, then this is the X prime, and here this is X tilde. I want on this X tilde to have some clause, the alpha tilde, whose restriction to the fiber over 0 tilde to be just alpha. Okay, so that's extendability. Then, yeah, it's a nice observation is that we have the proposition okay, so let's I from X to B be as above. Okay, now I take 0 to inside B. It's not just any point. This will be a very general point. This is a very general point. Very general. Okay. So if alpha inside H K X R, here this more K of course will be an even number to have an algebraic. If this class is algebraic, namely it's the class of some algebraic cycle, then alpha is extendable. Okay, then I can just sketch the proof. So now we have this class. I have a very general fiber. Okay, here I have a class which is algebraic. So then that means on this very general fiber, you have like an algebraic subvariety which represents this class. Then by spreading principle, then we know that because algebraic subvariety is defined sort of using finitely many conditions, what you get is you do get a B tutor like this, then and you have a point, okay, then this subvariety on this fiber actually spreads in the family, so you can have some sort of Z, which let's call it a Z prime, whose restriction to the fiber is the fiber is this kind of algebraic cycle you started with, and then this you can resolve this. This will be the X tutor, and you just take a sort of the strict transform, you get the Z tutor. Some exceptional devices, that doesn't matter. Okay, you can see that if you have a cycle which is like class alpha algebraic, then it's represented by something algebraic. Then over some finite extension, you can define that algebraic subvariety, so it spreads in the family. So in this way, you can see that the class is extendable because on X tutor, you just take the class associated to Z tutor, and that will do the job.
I mean, just a question.
Yeah.
If you intersect Z tilde with the fibers, how you guarantee that this family of cycles, the dimension doesn't change, or maybe it's a flat family, at the end you want to use its cohomology class? I mean, usually the controlling this behavior of families of algebraic cycles is not so easy, at least for me.
Well, indeed, if the Z you get can be very complicated on some special fibers, it can like jump the intersection have higher dimension also, or even it contains a component also. But on this very general kind of fiber, it's all fine.
So you will consider just the cohomological of Z tilde itself, not its intersection with the other fiber. Okay.
Yeah, on the total space, because it's smooth. Okay. Yeah, it's smooth. Then we can take the class. Then you can associate and can restrict to the fiber.
Okay. Okay. Yeah. Thanks.
Okay. So, yeah. Then that is kind of this gives you like a sort of criteria to check whether something will be non-algebraic. Because then if you can check some class which is not extendable, then it cannot be algebraic, right? So then the key non-extendability property is the following. The key non-extendability result. So I will put it as a theorem 6. Let X over B, which is P1, is be a Lefschetz pencil. F is Lefschetz pencil of hypersurfaces in Pn plus 1, where n is odd. Let an x, which is pi inverse 0, be a smooth fiber. Then every non-zero element alpha inside the edge in the middle cohomology of X with R coefficient, as long as the class is non-algebraic, it is non-extendable. Now, of course, because n is odd, this does not immediately give you sort of counterexamples to the integral Hodge conjecture, because in Hn there's no integral Hodge class because n is odd. But using this non-extendability result, we can cook up some other classes which is indeed Hodge class, and they are not they are non-extendable. So in this way, we conclude they are non-algebraic. Okay, so now we can. Yeah, so I will prove this non-extendability result later, but let's see how we can use this to cook up some non-algebraic integral Hodge classes. It was proof of theorem 3. That's the theorem where you have the alpha tensor U being non-algebraic. So now what we do is we take a so let's be a Lefschetz pencil. Okay. Now yeah, so I take a 0 to be very general. Okay, and I take X to be the fiber over 0, and alpha to be some class Gn inside, let's say, okay, I take Z coefficient. Okay, and if alpha tensor U inside edge n plus 3 X plus S with Z, if this is algebraic, then we will have the following. So we can extend this family. So okay. Okay, so okay, I just so this has roughly we will have this kind of diagram, and then we can do the resolution. Okay, such that on this X tilde across S, you can have some algebraic class which represents alpha tensor with U on the special fiber. Okay, so then we can have some Z tilde such that this Z tilde, you take the class restrict to X is alpha tensor U. So that's the extendability. Okay, now and what we do is we basically we take, so I take a V to be the H1 set S 1 2 Z. Okay, this is the class which corresponds to the étale double cover of the Enriques surface, and it has the property that the pair between this is equal to 1, so that they are sort of due to each other. Okay, so U bar, so U bar is U mod 2. But the U itself is two torsion, so it doesn't kind of change anything. Okay, now once you have this, then so what we do is let alpha tutor. So this defined to be, I use this z tutor, this class. Of course, now I mod 2. I consider z mod 2 z coefficient and use this to act on my v. Okay, then you will see that alpha tutor restrict to the fiber, it will be alpha. Okay, now you can see that if the alpha tensor U is algebraic, then it's extendable, then alpha will be extendable. That's mainly because the U is a constant. It only comes from the surface S. Okay, so once this tensor is extendable, you can conclude the alpha itself will be extendable. Okay, now then you get a contradiction because by the theorem 6, that's not possible. Okay, so this is how you use extendability to kind of construct counterexamples to the integral Hodge conjecture.
Maybe one question. The
Yeah.
fact that it's the Enriques surface, so far I see that you have used that H1 and H3 are torsion. I mean, you use something beyond this one?
No, not really. Actually, well, this Enriques surface is quite artificial. You can use
yeah, exactly.
any kind of variety. Well, if you can find some torsion element in order degree, and the dual element in the like a complement degree, and that will make the argument work.
Okay.
Yeah. Okay, now and I will say something about how we can prove the non-extendability theorem 6. So this is about vanishing cycles and base change. So first, I will show you a local picture. So now suppose I have this is over the disk. Okay, let's go to pi. So this is my x. It's now we are a bit in the like a complex analytic geometry setting. X will be a complex manifold with a proper map to the unit disk. Then general fiber is smooth, and the central fiber will be, has an ordinary double point. So that's the setting. So now what we do is I do the base change. This is z maps to z to some power r. Then if you pull back this family, you will see that it's still quite nice. The only thing is here, this becomes a singular point. Okay? You can write down the local equation, you will see this becomes singular. Now, what we can do is successive blow up several times, find it many times, then you will get something smooth. So I get this will be here. Maybe you have a lot of things like a kind of what's called exception divisors. So this is successive blow up. So you blow up the point. Again, you will usually get another singular point. You blow up again, and so on. So after finding it many times, you get a smooth. So this will be the x tutor, and this will be the x prime in this local setting. Now, nice thing is here, we have the notion of a vanishing sphere. So that's a vanishing cycle on the nearby fiber. It's a topological cycle. It's just a sphere, but when you move towards the central fiber, it vanishes to the point. So that's a sort of geometrical picture of this vanishing sphere. Now here you can still say I take some image of the sphere, and you will see it will vanish to this singular point. Now, if you do the blow up, it will again get to sphere, but it vanishes to some of the, well, it not necessarily vanish, but it will specialize to some cycle on an exceptional divisor. That's the kind of the exceptional divisor of the last blow up. So the key is the vanishing sphere. So on X tilde, the vanishing sphere there's specialized to a cycle on some exceptional divisor. Okay, so this is something you can compute it kind of directly. Now, then those, because this singularity is actually you get is quite simple, then you can explicitly see that the exceptional divisors are quite simple. The exceptional divisors they are basically either smooth quadratic or like a P1 bundle. So P1 bundle over smooth quadratic. So as a consequence, they have their homology vanishes in order degrees. Okay, so now you can see that my vanishing sphere, it's specialized to some like a topological cycle on the exceptional divisor, but as a homology class, it should be zero there. Now, as a consequence, so you can see that so the vanishing sphere has zero homology class in this desingularization. Okay, this is the local picture. Now we can globalize this. So I can take a global. So that's the okay. So now I take a Lefschetz pencil. Okay, so this is a Lefschetz pencil. Okay, now of course it will have some like critical point values, but my zero, the point is here. Okay, so over each of these you have some. So this is the fiber. Okay, so let's say this is BI. Correspondingly, you have the fiber XI, which has an ordinary double point. Then associated to that, nearby, you have a vanishing cycle, and but you can pick a kind of path from this 0 to the BI, and along this path you can transport your cycle to something here. Well, it might be not be so local, but it's a topological cycle on the fiber. So this will be the delta associated to I. Okay, so in this way, so first the Lefschetz theory tells us that the Hn of xz is generated by this delta i's. So delta 1 some n, so depends on the number of singular points as singular fibers. Okay, so the whole homology group is generated by vanishing spheres. Then here we use the condition that n is odd, because the whole homology group will be like a vanishing homology. Okay, so that's something. And secondly, so then once we have this, then we can see that now, so this is the P1, the B, which is isomorphic with P1. So now I have, this is my X over B. Suppose I have some B tilde, a generic finite map, and I do base change. This is X prime. Now this might be singular, so I desingularize, get this. And here I have a fiber, and I can pick something living above. So this is a zero tilde, which also survives inside here, because the generic fiber does not hit singular points. Okay. Okay, now you have this. Then as a consequence of the local computation, we see that, let's call this to be the injection I on tilde. So I tilde, so this is a consequence of local computation. I know Hn from X, Z to Hn X tilde. This is 0. Because Hn is generated by vanishing cycles, and all those vanishing cycles on X tilde actually vanishes as a homology class. So this will be the 0 map. And this computation, or not just for Z coefficient, you can do any coefficient. It's still 0. Okay. Okay, now we are almost there for the proof. Because okay, now let me do, on the last page I can proof of theorem 6. So we take alpha inside HK X R. Okay. Now assume that alpha is extendable. Then we can construct this B tilde and X prime and X tilde and so on. So in the end we get X tilde, which is HK of okay, so this is the big X, and the X tilde with R coefficient such that alpha is equal to alpha tilde restrict to X. That's nothing but you pull back the alpha tilde along the embedding of X into the total space. Okay. Okay, now let's call it beta H n X. Okay, then we can compute the alpha, the pairing between alpha and beta. So that's alpha is a homology class and beta is a homology class. We do this pairing. Yeah, maybe we just base change. Okay, I also will consider R coefficient, so which is the okay. Then I take a pairing on X. Now this is nothing but this is I tilde per bank of I beta is on X. Okay, that's the same as what? Take alpha tilde without the pulling back, but now I this push forward beta. this is evaluation on X tutor. Now this is alpha tutor, but we know that I tutor push forward is always 0, so this is 0. Now you can see that this holds for all beta and forces alpha itself to be 0. This says alpha is equal to 0 in H in X R. Okay, so and it says that 0 is the only clause that is extendable in this setting. Okay, so yeah, so that's all I would like to say. Thank you very much.
Okay, thank you, Mingmin. Yunus, I think we might ask in the informal session of, you can stop recording. Just a minute.